Okay, today's work is coming out of 8.3, and we're going to be dealing with rational functions, these fraction equations that have a little bit beefier or meatier equations. So there's a little bit more to them. First thing I want to point out is on your assignment, I'm actually going to just start with question 7. The first few questions are really built for maybe in-class work, but if we start with question number 10. Okay, 10 is going to ask us for a couple of very specific things. It starts with x squared minus 7x minus 60 all over x plus 3. And we're not actually going to produce a graph of this, but we are going to answer a couple questions about it. First thing we're going to look for is x-intercepts. Now when we do x-intercepts, I'm going to draw a quick sketch. The idea of an x-intercept is that it somewhere, crosses the x-axis. In other words, the equation as a whole, and of course this was a y equals, the y is 0. Okay, so the equation equals 0. That's what we're asking is, when does this equation equal 0? Well, here's the thing. I can't divide by 0, so x plus 3 equals 0 is not going to help me with x-intercepts. But if the numerator turned out to be 0. Say it was 0 divided by any number down here. It doesn't matter. But if it's 0 on top, 0 divided by anything is 0. So when we look for x-intercepts, what we're really doing is taking the numerator, x squared minus 7x minus 60, and asking, when does it equal 0? Because if the top is 0, then the whole thing is 0. So that's our first half of the assignment. It's all about making the top be 0 to find the x-intercepts. And so this is a quadratic. We could use a quadratic formula. We could try to graph just this and look for its zeros, but we can also just try to factor it. And these should be pretty easy to factor. X and x, plus and minus because the 60 is negative. Factors of 60, there's 1 and 60, 2 and 30, 3 and 20. I'm looking for a difference of 7, so none of those. 4 and 15. No, 5 and 12. And 5 and 12 is going to work for me here. I want the 12 to be negative and the 5 to be positive. So that means there's going to be an x-intercept at negative 5 and positive 12. What's really cool about this is if we take either of those pieces of information and plug them back into the original problem, the numerator becomes 0 and the whole thing becomes 0. And if you want to graph this in a graphing calculator, it would be a good way to check. You would be able to see, yes, when the top is 0, the whole thing is 0. Then we just have one last piece of information we're being asked to find, which is where are the vertical asymptotes? Okay, vertical asymptotes we did before in 8.2 was all about essentially the domain restriction. And so you remember from 8.2, we would say x does not equal, and there was a number that x didn't equal. And when we studied that last time, it always had to do with denominators cannot equal 0. So we don't know how to divide by 0. It's physically impossible. So up here, we're asking the question, what x value would make the denominator essentially 0? So we look at this and we say, if I used a negative 3 plus 3 would be 0. And it wouldn't matter what happens on the top of the equation, only the denominator. So here, the denominator would be 0 if x is negative 3. So I'm going to say x does not equal negative 3. That's the denominator restriction. So the actual vertical asymptote would be at x equals negative 3. Now when I say, obviously I can't use negative 3, but this is the vertical asymptote, okay, which means that over here at negative 3, I'd have a dotted line. That's what we're being asked, is where does that dotted line go? It goes where x is negative 3. Okay. So the domain is x doesn't equal negative 3. The vertical asymptote is that x is at negative 3. So try not to get those confused. I know a little double talk. In 1 second I'm saying that x is not negative 3. The next second I'm saying that it is. But that's what you're going to be asked to do for that. Give me the zeros from the top. Give me the zeros on the bottom. As the top, it's the X-intercepts on the bottom, it's the vertical asymptotes. There can be more than one. You might have more than one. You might have none. If the bottom never equals 0, then there are no vertical asymptotes. We'll look at some cases like that. Let's look at question number 15 next. And I'm going to use my calculator to help me out here. 15 has 2x over x squared minus 1. Okay, so first thing I want to distinguish as I go to do this graph, okay, I want to find what's called the horizontal asymptote, and then I want to find the vertical asymptotes. Those are those boundary lines that we drew in 8.2. So horizontal asymptotes, in the last couple sections we talked about different scenarios. If it was like 3x over 2x plus 1, minus 4, something like this, we would use the coefficients. And we'd say it was 3 over 2 for that horizontal dotted line. Here today, though, you'll notice that the exponents don't match. This is x to the first over x squared. Anytime the exponents match, we use the coefficients. If, in cases like this, the biggest exponent is on the bottom, I'm going to call this bottom heavy. If it's bottom heavy, the horizontal asymptote is always at x is 0. It's always going to default to that because the denominator is getting big faster than the top. That makes it bottom heavy. If you think about taking 100 divided by 1 billion, that 100 suddenly seems so insignificant, no one gets anything. So we're letting the bottom get big fast. So it's bottom heavy. Anytime the exponent is bigger on bottom, the horizontal asymptote is always 0. If it was the same, if it's squared and squared, we use the coefficients. Okay. Then with the vertical asymptotes, remember we want the denominator to be 0. Well, x squared minus 1 factors as x plus 1 and x minus 1. That would mean that I'd have a vertical asymptote at -1 and at +1. This horizontal asymptote, it's a y value. Sorry, y equals 0. Horizontal lines would be y equals. That's my fault. But here, horizontal is -1, +1. Don't be afraid to accept your mistakes. Take ownership of them. All right. So what I need to do right now is I need to draw these asymptotes in. I'm going to come in and at y equals 0, I'm going to draw a dotted line. Okay. Generally speaking, that's the line I don't touch that I come close to. The next piece I need are the vertical asymptotes. So over here at -1, I'm going to draw a vertical dotted line. And over here at +1, I'm going to draw a vertical dotted line. At this point, I'm just going to use my calculator to help fill in the 3 areas. You can see one on the left, one in the middle, and one on the right. I need to know where does the graph exist. And these are all dynamic, and you can't say that they're always the same. And so you really just have to graph them. So I'm going to do parentheses, just for safety, I'm going to do parentheses around the numerator, out of habit, divided by parentheses around the denominator, x squared minus 1. And I'm going to graph. And my graph looks a little funky. If you've got a calculator that's a little bit newer, it'll look nicer. I'm going to just change my viewing window just a little bit. Right window. I'm going to go from -5 to 5 on the x scale, and that I think might help. Yeah. Okay. So again, my graphing calculator is older, and it draws the vertical asymptotes in for me. It shows me where those lines are. So those are the lines, and then of course here's this. But you can see there's 3 pieces. There's the curve that's down here, the curve that's up here, and this is unique to this problem, or to this new set that we're working on. It's got a zigzag through the middle. And so your graph should look like this, and you're done. Okay? A lot of these are coming straight off the calculator, but we do want to know where the boundaries are, where are those types of pieces of information. All right, I just have 2 more questions for you, and then you're going to be done. Let's look at 23. 23 is a special case. Okay. 23 has the equation h of x, or y, equals 3x squared plus 10x minus 8 all over x squared plus 4. All right. Now notice that x squared and x squared the exponents are the same, okay? So we're going to default to what we did in the past. This is 3 on top, this is 1 on bottom. So for my horizontal asymptote, I'm going to say that y equals 3, or 3 over 1. Okay. Because they're equal in exponent, I can just use their coefficients. Then when I come to the vertical asymptotes, remember, we want the denominator to be 0. So I minus the 4, x squared equals negative 4. Taking the square root, I put a plus or minus. X equals plus or minus. The square root of 4 is 2, but because it's negative, it has an I. Well, 2i is imaginary, and that's not part of my normal graph. So I'm going to say that this has no vertical asymptotes, or none. Okay. Well, what does that mean? If it doesn't have vertical asymptotes, what does this graph actually look like? It's actually going to be very unique and dynamic. The reality is that without a graphing utility, we would have to plug in probably about 40 points to really get a sense of how this curves at different locations. We could probably do it with a little bit less than that, but if we want a really accurate, smooth curve, we'd have to have a lot of points. So what we're going to do is we're going to scrap that idea. We're going to go straight to the calculator with the information we have now. Okay? I'm going to go ahead and draw a quick sketch. There are no vertical boundaries, but there is a boundary up here at 3. Now, horizontal asymptotes at times are allowed to be crossed, to be touched, but they give us an idea of where the graph is as we go to the very far edges. So this is going to look a little different, but it's what happens when we allow graphs to be dynamic and to have oddities. Like this does not have a vertical asymptote. So what does that do to the graph in general? All right, so we're going to start parentheses. 3x squared plus 10x minus 8, close parentheses, divided by, parentheses, x squared plus 4, close parentheses, and we hit graph, and look at that weird thing. I'm actually going to hit zoom 6, and we see this weird, it's almost like a check mark coming in. And here's the part that's a little hard for students to accept, is if I draw that boundary line in right here at 3, you can see that it flattens out at 3 on the edges, but through the middle it crosses along the way. That's the dynamic nature of these equations. We really do want to use a utility to help us with this. So I'm just going to do the best I can to follow along. Okay, it looks like I'm below, and I do this check, come above, and then work my way back down. And there's the graph for 23. Very unique, definitely dependent on a calculator. We use that kind of a tool. But those are the, I mean, we're really going to use calculators a lot for this. But knowing where your asymptotes are, things like that, are beneficial. We do have one last question I wanted to look at with you. It's the word problem. I wanted to look at question number 31 with you because it's a significant problem for farmers as they try to keep their bales of hay dry and clean. So we're going to look at 31. And in question 31, we told that a farmer makes cylindrical bales of hay that have a volume of 100 cubic feet. So it's important that we understand volume equals 100 cubic feet. And so we're talking about a cylinder here. So you can imagine there's this cylinder of hay, there's a round bale, but they're going to cover it in plastic to try and keep it dry and keep it safe. So we want to use the volume of a cylinder, and we want to write an equation that has the length of the bale in terms of the radius r. All that means is we want L alone when we're done. Well, first off, the volume of a cylinder is pi r squared. And then usually we use an h, but here they're using L. So we'll use L for that. We need to get L alone. So I'm going to divide by pi r squared. If I do that on both sides, those are gone. Also, I know that volume is 100, so I can plug that in. So for part A, my equation is that the length of the bale, okay, needs to be 100 divided by pi r squared. And you notice the r is in the denominator, which means the bigger the radius, okay, the smaller the length has to be if I want to stay at 100 cubic feet. Okay? And so there's my equation for that first part. The next piece, okay, for part B, is to write a function that gives the surface area. Okay? Okay, now surface area is a little bit tougher to come by. You have to understand that to do the surface area, okay, for surface area, it's the circular piece on each end, and then that wrap around the middle. So the surface area is 2 pi r squared. That's this area and the area on the other side. Okay, so there's those two pieces. Plus, I have to add in the sides. Okay, or the side as it goes around. And the side as they go around, okay, is the circumference, the distance around, times the length of the bail, or the height of the bail. And so the circumference is always pi times d, or 2 pi r, so 2 pi r times L, okay? So 2 pi r L. But, okay, I don't want, I want it to only be in terms of the radius, okay? So instead of writing L here, okay, I'm going to take this equation and plug it in. I'm going to do a little substitution. And so S is now 2 pi r squared plus 2 pi r times 100 over pi r squared. Well, you'll notice a couple of things. Your pi's cancel, one of the r's cancels, and so our final equation for the surface area of the bail is 2 pi r squared plus 200 over r. Okay, so we now know we have an equation for that. What it asks us in part C is to find the dimensions of the bail that has the given volume and uses the least amount of plastic when the bail is wrapped. So what that means is we want the smallest surface area we can get, okay? We want a minimum for this down here, so minimum, and so that's what we're shooting for, is where is that the lowest, okay? And so I could graph this to do it, and that wouldn't be too horrible. Maybe we'll do that eventually anyway. But what I really want to do is just talk about, can we make this small? The small, see, oh, you know what, there's a pretty tough balance there. We'll have a hard time deciding exactly how to do it. Let's go ahead and graph it. Let's see what the picture really looks like, and then we'll be good to go. Let's turn it on, y equals, figure this out. So we're going to go 2 pi x squared, right, plus 200 over x. We're going to graph this. Okay, now I don't see much here, right? Now we know that the radius can be anywhere from 0 to a large value. The surface area, though, which is what the y value is going to be quite large. So what we need to do is we need to change our viewing window. So I'm going to change my viewing window as the smallest radius would be 0, and the biggest radius, let's say, you know, we can stick with 10. 10 feet radius is a huge bail, so I'm not too concerned about that. My y min, though, the smallest surface area would be 0. The biggest surface area, this is where we really have to do some guessing. We've got 200 as a number in the problem. Let's say that we, let's throw 6, let's throw 1,000 at it. I don't really know, but we'll see if we get some picture to show up. And the scale, let's count by 100. Now if I look at the graph now, oh, see, now we've got a beautiful curve here. We're really seeing this dynamic curve, and we just want the minimum. So what I'm going to do is second trace. I'm going to look for the minimum. We've done this before. It says left bound, so I need to go all the way until I know that I'm on the left side of the lowest point. So right here, I'm coming up, so I like that spot. And now I need to go to the right. So I'm going to scroll over here to the right. I'm going to hit enter and ask it to guess. And it comes up with a minimum radius, or x value, of 2.5. Specifically 2.1515. So r equals 2.515 feet, and we're going to plug that back in right here for r. 100 divided by pi times 2.515 squared to get that the length of the bail should come out to be 5.032 feet. So now we know how big that bail is, and you know how big do they stack. Those kinds of questions can all be answered that way. Hopefully that helped you get through the assignment, get you going. Remember, most of this is going to be calculator dependent or calculator driven as we graph, but you are looking for those horizontal and vertical asymptotes when they occur so you can get a good basis of where your graph is. Good luck.